This works. So, good morning, everyone. For the people online, can you hear us? Send a message in the chat. So, welcome everyone. I see still people coming. Of course, every time we start at 9, in principle, we start a little bit later, but today we have quite a number of people online. We expect around 90 people online. So we have to keep the time. So I start with the house ruling. Please keep the time. So I'm Fausto Dallucci. I'm working, well, for OneCube, for Eindhoven University of Technology, and since yesterday also from Zephyra. So a bit busy. But today I'm here as OneCube, organizer of this event. But before we start, I must say that the event has been organized thanks to 13 projects you see everywhere. So I want to thank the coordinators for joining us, very enthusiastic with a lot of ideas. And at the end, we did quite a nice setting for the time being. I hope that the room will be busy soon. And of course, these are European projects. So we have to thank the European Commission because at the end, we are able to give this type of workshop for free, thanks to the European Commission. Now, today, what we plan to do is to show results related to the projects. The projects are about sustainable technology and circular technologies, so you will see a lot of results from the projects. But the idea of the workshop is, of course, to interact with the people from the projects. As a matter of fact, probably the people in this room will be your colleagues or partner in the next calls in February or in April. So take the time really to networking and with your colleagues. And of course, to also make questions. As I said before, we would like to keep the time. Please put the presentations in one computer because that is much easier to share with the online people. And of course, we have to thank also Gaetano Anello and Valentina Cecchetto for the help. Without you, it would be a bit difficult to do all this. For the people online, if you have questions, put on the chat, and then Gaetano in this room or Valentina in the other room will read for the presenters. Then a few more rules. We have a lunch. It's at 1 o'clock. Now be aware that this building is the complete building has rooms for meetings, which means that each meeting has lunch. So if we go before 1, perhaps we are taking the lunch from somebody else, and then our lunch will be thrown away. And since we are doing circular and sustainable processes, I think is not the best visit card. So let's go at 1 o'clock. Of course, there is coffee every time. You can go freely. There are all kind of drinks without alcohol. Then today we have a dinner here. On the program is written at 6, but actually we will start at 5:30. Also because during the dinner there will be some music played by a young orchestra. So we hope that will be a nice event. For the people that may need certificates of attendance, if you need it, just say at the registration, and then later we will send via email. And finally, for the people that came by car and parked here, downstairs there is a parking place. If you have the ticket, you will get 35% discount just passing by the counter. Okay. And with this, I think we can start. And it's my pleasure to start with the first keynote speaker. Actually, plenary speaker, sorry. Is Professor Michele Aresta. We are going to put the presentation. Perfect. So, Professor Michele Aresta, I mean, if you ever worked with CO2, I think you should know this name. when I start doing my master, I already read papers of Professor Michele Aresta. So it's really a well-known professor and researcher in this field. So Professor Michele Aresta, please come. And let's welcome Professor. I will give the floor to you. Please use the microphone so that you don't mind.
Thank you very much, Prof, for the kind introduction. It's really a pleasure for me to stay here with you, so many European projects, and speak about circularity, especially carbon circularity, which has been my target since many, many years. And okay, we start immediately with my presentation. It's a short trip in the field of why we need to use CO2 as a source of carbon. So what I intend to do is just to show that CO2 is a very key source of carbon, because the other alternatives we have, biomass, is not limited. It's quite limited indeed. Maybe we are already overusing biomass. And so we can use CO2 in many different ways, as a building block for chemicals or materials, or as a source of carbon for fuels, to quite different approaches. Can make e-fuels and solar fuels from CO2. We shall go to that area. And I focus in the final part on the selectivity issue in converting CO2 into fuels, energy products, especially using photo and photoelectron catalysis, because I will focus on solar fuels in the last part of my talk, which is the topic of one of the projects, which is the design project. And then I will cover a little bit the calculation experiments to show how it's possible to engineer catalysts for the selective conversion of CO2 and water into energy products. So that's the trick we have to do. So this is a reality. 200 years of linear economy have shown that our planet has not infinite resources, not only, but has not the capacity of recovering from all the impact we are creating on it. So that's the need we are of developing a circular economy, and especially a carbon circular economy, which will bring to a man-made carbon cycle. So I will not use labels like artificial leaf, artificial tree, which are not reality for us. It's just a man-made carbon cycle that we have to develop. Why we need carbon? Cannot make without carbon, this is sure. So there are two words which very often are used as synonyms: decarbonization and defossilizations. They can't be used as synonyms, they are completely different meaning. We can defossilize the chemical industry for what concerns the energy used by in chemical industry, but we cannot decarbonize chemical industry because the chemical industry needs carbon, needs a lot of carbon. And that's the amount of carbon that we use today. These values are billion tons of carbon, not of compounds derived from carbon. This is the amount. These are chemicals derived from their polymers. Olefins are not considered in this list. They are there as polymers, the end products of them. So altogether, we need 700 billion ton carbon as 2022. And the forecast is that it can grow to 1 gigaton of carbon by 2040. Cannot do with that, absolutely. So we need that. Also, the steel industry needs carbon. The transport sector needs carbon, sometimes something like 700 million ton carbons again per year. The agro especially and maritime together makes that, they make that. So not considering fuels for land transport, we need something like 1.5 gigatons of carbon per year. So assume that you want to cut out fossil carbon. Don't want to use any more fossil carbon. Where do you get this carbon? We have two sources, biomass and CO2. Waste plastics, they are not contributing new carbon. They need new carbon. So that's the point. Biomass. There's a lot of expectation on biomass, but the reality is that over the total production of biomass world level, we are in this condition, only small part of that, 1/3, is land-based. Yeah, the rest comes from water cousins. So we are investing this amount, 16.7, almost 70 gigaton per year, which is used mostly for food and feed. Only this small amount is used for energy production, 1.3 gigaton per year. It's just less than 10% of it. We cannot increase this one, maybe. But the problem is the sustainable biomass harvesting. There are people who say that this is set at 8 gigaton per year, and we are already at 16 gigaton per year. Then we really expand that value. That's a problem. We have to find a solution to that. And we need new technologies, and we have to go to the integrated biorefinery approach for the correct use of biomass. So there is a limit in biomass. There is an hope on biomass again. The valorization of waste-to-wet biomass, making biogas. This conversion is very limited today. The overall production is around this figure here, 70 billion cubic meters per year, and the potential is much higher, is 7 times that. So if we make biogas, 40% of it will be CO2. So we will increase the amount of CO2 which will be produced. This is called biogenic CO2. This is green CO2. It's something that can be very easily recovered at low cost, because there is a high concentration of CO2 in the stream. It's much better than collecting CO2 directly from the atmosphere. Cost is much lower. So that's a source that we have to keep in mind, but still it's not a limited source. It is quite a limited one. Polymers, they are not really contributing new carbon. They need carbon every year. They need 40 million ton carbon, new carbon every year. Assuming that we are able to recycle the entire amount of waste plastics. Today we are at 9% only. So there is a lot to do in that area too. So that's why CO2 plays a key role. And I'm convinced of that since a very long time. Very, very long time. I'm pushing in this direction since decades. And now we have some political positions on this issue. First time. European Union, they plan to use something like 200 billion tons of CO2 by 2050. 250 million tons will be used in the CCS, in disposal in the oceans or on the ground, where you want. So the political position influences investment and industry involvement. This is an important point. So if there will be a clear position from the European Union, most likely investment in the area of using CO2 as a source of carbon will increase in the future. I hope so. As a matter of fact, I continue to say that CCU is a strategic manufacturing technology for the future of our society. Let me remind something. This was the first ever reported nickel complex in which a molecule of CO2 was coordinated to nickel 50 years ago. And since then, I'm pushing in this direction of using carbon dioxide for making chemicals, or using only the carbon atom. So already in 87, we were there. This was a NATO school. 100 people, young people working on this, carbon dioxide as a source of carbon. At that time, there was an interest in this area because the coordination of CO2 to a metal center completely changed the property of the molecules. It was possible to deoxygenate CO2 at room temperature, which does not happen at all when you use the free molecule. So that was a very important message to the catalysis society. And since then, people started to investigate the possible conversion of CO2 into chemicals, polymers, and fuels also. And in the 1890s, we had a lot of knowledge of this process, a lot. When there was a crisis in the 70s and 90s, CO2 came out again as a source of carbon. Then there was no need for using CO2 because the cost of oil and coal and the gas was so low that it was not necessary to recycle CO2, which is a costly procedure. And we forgot about CO2. We forgot about CO2, about all the knowledge on the conversion of CO2. Polymers from CO2 were already known at the end of the 70s, using CO2 as a common word. Converting CO2 into hydrocarbons was already known at that time. Methanol was already a pilot plant, 50 liters, made in Japan. So we are speaking about 40 years ago. Then this field was completely abandoned. A few groups around the world, they insisted on that development knowledge. The knowledge is knowledge today is a basis of the new approach to the conversion of carbon dioxide into chemicals, materials, and fuels. Okay, we have that. What we can do with CO2. In the upper part, you see the use of CO2 as a building block of chemicals. This means that you are not converting CO2 immediately. You just include this CO2 into a material as it is. So you don't need energy, you don't need hydrogen. You just use CO2 as a brick for building a wall. And this is true for making many different polymers. That's a very important message for us. In this kind of chemistry, the chemical industry today uses 220 million tons per year of CO2. And the emission is 930 million tons of CO2 per year. So the chemical industry is recovering carbon at a rate of 23.7%. It's one of the highest rates in the panorama of circular economy. It's curious is that most of that CO2 comes from the ammonia production. And this is most of it, 180 million tons, is used for making urea. So that's a very interesting concept. You see that the recycling of carbon is not something new. It's there since the end of the 1800s. So that's the message we have to learn from the past. In the lower part, you will see reactions in which you need both energy and hydrogen, the conversion of CO2, because you are putting hydrogen into all products there. So the issues are where you get the energy. Cannot be fossil-based, must be perennial energy, solar energy, wind energy, hydro energy, whatever, but not fossil-based energy. Otherwise, you will produce more CO2 than you will fix. So that makes no sense. And you need hydrogen. Hydrogen cannot come from steam reforming or methane. Must be from water. That's a big change. That's a big change which next generations have to face and win. That's a real challenge to win. They have to find a way to use water as a source of protons and electrons for the conversion of the CO2 into energy products. From time to time, I will show some publications we have done in this. So it's obvious that the market of energy products is much more large than that of chemicals. Okay, so that's why there is a lot of interest in conversion of CO2 and water into this kind of products. That's the big change we expect in the near future. This is the old way, linear economy, fossil carbon to emission of CO2. Now we want to collect water and CO2 from the atmosphere using sun, combining all the technologies we know, and produce the same product we have through this way. So that's something which is very challenging, but we have to win this battle. Otherwise, we will suffer very hard times. Okay, so we have several ways for the conversion of CO2. We can use thermal catalysis using hydrogen. We can use electrochemical routes in which hydrogen is not needed. We can use photoelectrochemical processes in which we use directly the solar energy for CO2 conversion instead of producing first hydrogen or producing first PP. The situation is that methane steam reforming, the cost of hydrogen is the lowest one today, and will be for a long time. Will be like that for a long time. If you want to use electrolysis using nuclear, is a little bit higher. You have a range because it may change according to the regions. If you want to make electrolysis, then the cost rises, but there is a huge limitation of materials. That's the big problem. If you want to make electrolysis with photovoltaic, then that up to 4 times higher. If you have an hydrogen which costs 4 times higher than natural, this means that all cost of derived products will rise. This will be a huge impact on the economy. So this is why you cannot apply that today for production of large volumes of goods. The same with wind. So this kind of productions of hydrogen today are completely out of market. You can't subvention, you can do what you want, but you will never reach the possibility of having them on the market at a very large scale. So you have to reduce this price. The expectation is that by 2040, can increase the photovoltaic efficiency, the solar to electrons conversion, rising from 20 to 40%. So we double the efficiency, and we can lower the cost of the materials. So in this way, this cost will be reduced. While this will be a little bit increased, because at the moment there are countries, Europe is one of those organizations in which you can use this technology, but you have to capture CO2. Capturing CO2 will rise the cost of production of hydrogen necessary. And you remain with the problem what we do with that CO2. Okay, so that's something that we have to keep in mind. Anytime we want to improve a technology, we have cost to the production of that good. And so that has a strong impact on the economy. So maybe that by 2050 we shall reach the target. It's a big question mark. I don't know. I really don't know because there are some limitations to the availability of materials for producing such huge amount of hydrogen we are speaking about. And we see these days how political situations can really block the growth of our technology, the expansion of our technology, the exploitation of our technology. That's a very hard barrier. So we have to halve the cost of green hydrogen, and we have to double the solar to efficiency, to electricity efficiency, in order to make the electrolysis with PV advantages and vital for the use of hydrogen. So there is another approach that's, I said, the direct solar utilization in CO2 conversion. This is something that we have been experiencing since a long time. This was the first reaction reported of CO2 insertion into a carbon-carbon bond under UV light radiation. Then we went to the carboxylation reactions, then to the reduction of CO2, not very selective. We coupled CO2 with also enzymatic catalysis using light for recycling of the cofactor. This is a trim reaction from CO2 and water to metal at room temperature. That's fantastic. But the cost of the cofactor is such that it is completely out of any possible application. The cofactor, 1 gram of that costs as 1 ton of that. It's impossible to work. Okay, so we have been working in recent years on the production of energy products from CO2 using some composites, usually some PN junctions, direct irradiation of CO2 and water. We have reported some interesting results, like in this case, coupling zinc oxide and copper oxide. They make mixed oxide, double mixed oxide, and they modify both the reduction reaction potential and the oxidation reaction potential. And so we were able to produce either hydrogen in the absence of CO2 or methanol in the presence of CO2 with no hydrogen production. So the reaction was very, very interesting and selective. We also tried to use PN and N junctions, in this case, indium and carbon nitride. And the reaction was not very selective. But anyway, the junction, this very curious junction, allowed conversion of CO2 into methanol and methane, which was some interesting curiosity, not very interesting from the rate of application. So in our project decided, I go to focus on this part, my thought, this topic. We were working on biosilicates as a support of our photocatalysts. Photocatalysts were based on copper oxide, copper monoxide. And we want to use this biosupports instead of the lights. But the very interesting fact, finding very new, was that when using these biosilicates, which are the silica skeleton of microalgae diatoms, so they can find in the sea, not a single species, but mix of, but you can grow in the lab very selective species. So we grow these three different, the technical name of this biosilicate is fructose. We grow these three different systems. This is a monolayer, very interesting. This is a bilayer, you can see the double layer here. This is also a double layer. And what we found was that according to the frustum we used and the geometry of the frustum, we could change the facet of copper 1 oxide from cubic to octahedral to rhomboidal. This was something very interesting because the three facets have completely different properties. So we became very much interested in that, trying to understand why this was possible and how it was possible to address the production of the facet in this or that direction. This is very important because they are completely different photocatalytic properties. So that's just to show what happens. This is the first one, and this is down here, FTO. So you can deposit the frustum on FTO, and then you make a deposition of copper oxide through photoelectrochemistry. So what happens is that you see very clearly when copper oxide grows on FTO, it is 11100 is a cubic. When it grows on the frustum like that, it becomes a 110. So that's there is an influence of the frustum on the facet. It's quite a huge difference between these two. And if we change, we go from this frustum to the other one, which I showed before, this one, which is called navicula, you have the octahedral. So you can make a selective production of copper 1 oxide according to the frustum you use. And why this is important? Why this is important because these three different facets have completely different properties. And what we found was that this one is known as a scarce activity because of difficult charge surfacing. Using 111, we could produce methanol quite selectively. Using the 110, supported on the frustums, we went to ethanol, but also to ethylene. So that was very interesting and curious for us because, oops, it's happening here. Okay, good. Because when you compare the copper-copper distance in the different facets, you find very unique figures. In 100, you have a copper-copper distance of 425 meters. In 111, it goes down to 370. In 110, you can go down to 260. So you are changing a lot the distance between the active catalytic centers. So the question came to our mind, how the distance of the active catalytic centers influences the formation of the product. You may have a C1 molecule or a C2 molecule. If you want a C2 molecule, you must have two carbons such a distance that the coupling is possible. So that's why we started DFT study in order to understand how the distance was influencing the production of different products. And this is a short story of the results we found. So this is our catalyst here, copper. Okay. The first one on the left is the structure of selected number of copper sites. This is a continuum surface, so there is not a limited surface, it's a continuum one. And you see how CO2 is coordinated in these 2 years. You have a O2 eta 3 coordination. All 3 atoms are coordinated to copper atoms. And this is an entering CO2 linear, still linear, the interaction with copper through the oxygen. So once you start with the transfer of protons and electrons, you make the protonation of this oxygen here, and the electron goes to carbon. And so you are making the carboxylic group. This is something we found many, many years ago in '88. This was just the first example of proton plus electron transfer to a coordinated CO2 for the carboxylate formation of the carboxylic group. So we found again that we can demonstrate that this is correct. Once you have done that, you have the reduction of CO2 to CO. These two do not couple. You need to make further reduction of CO2 to the forming group. And at this point, it's possible coupling of these two moieties. This is more or less reported into the literature. Let's see the thing. We have evaluated the energy for the barrier for the carbon-carbon coupling, and that's the value 13.6 under the operative conditions we use in our system. That means temperature around 40 degrees maximum in the electrolyte. And this makes possible the formation of the C2 moiety. The distance, that's important, is around 250 picometers, the copper-copper distance, in order to make the coupling. That's a very key figure. That's another very important information we got out from our studies, CFT studies. There is the possibility of an isolation of this. We get the here, we can get that. The oxygen goes to copper. And you make this C2. This is ethene. This is ready to leave as ethene. And in that way, if you go to the protonation, next step, in this case, protonation will occur at this oxygen because the transfer of oxygen to the copper lattice has increased the oxidation state of copper. So you need to reduce it in order to recover the catalyst. So you will make water from this with 2 protons and 2 electrons, and you release ethene. In that case, you go to the protonation here and here, and you will release ethanol. This is a common step where you can switch in the direction of making ethene or making ethanol. That's something quite interesting, and we are using this information now in our new photoelectrocatalyst in order to improve the selectivity. Selectivity in photoelectrocatalysis is a key step. Because if you make a selective reaction, if you at the end of the reaction have to separate liquids and gases, you will need energy for that separation. So at this point, we will almost cancel out the benefit of recycling CO2 because the amount of energy that you need will most likely consume all the energy that you have produced, which is in the reduced carbon product. So selectivity is a very key factor. Should have reactions which produce only one liquid compound, and one gas compound, or one liquid, one gas, which can be very easily separated. But whenever you have nations, you lower the value of the fuels you are producing. You are targeting energy-rich molecules. So we have also made an attempt to understand if it is possible to use a single site for the coupling of the carbons. We have forced this geometry here in which the formula and the CO are on the same copper. This is forced, really forced situation. When you release that, you go there, and you see that the two are on two different coppers, and this is 25 kilocal lower than that. So that's a huge energy. So that means that the single atom catalysis, in this case, does not play really an important role, at least under the conditions we are working through them, close to root. So that's a 25 kilocal difference in this, which is much higher than the activation energy in coupling on multi-site catalysis, two-site catalysis. So that's something interesting. And so we have investigated what happens if we push away carbon atoms. So here we are at 110 facet distance, 250 micrometers. If we move to 370, which is the 111, the transition state energy rises a lot. If you go to 400, get that the energy of the transition state is so high that will never happen under the conditions we are using in photoelectric catalysis. May happen in thermal catalysis, not under the conditions we use normally in photoelectric catalysis. So we, at this point, went up to an exercise. So we said, let's build a back. Let's build a backbone at the twin set of copper atoms. So let's put together two copper atoms at the distance that is obliged, forced. And this distance was 260 nanometers, as the distance we have seen is the best solution for carbon-carbon coupling. So we built this copper oxalate. We have characterized the copper oxalate, and we have supported this copper oxalate on carbon nitride. It's known that carbon nitride modified with metals can completely change the photoelectrical properties. So we have done that by high energy gallium. And we have shown that this system is quite stable, can use for several hours, and that there is no change in the FTIR spectrum. The distance is exactly what is needed for the optimal coupling of carbons to make C2 moieties. This is how the bang up of the nitride is modified by loading the copper oxalate on it, so in a very interesting area. We have shown that the copper oxalate induces photocurrents much higher than if you load iron oxide on it. And this is what we found, that under pure photochemical conditions, we can produce either acetone or ethene. These were isolated and identified using NMR, carbon and proton NMR. And this is interesting. This is the starting material. We have only copper one in it. And after 16 hours of utilization, some of it has been changed to copper 2, but just a small amount. So that means that photocatalysis is quite stable under the operative conditions. And there is no formation of C1 species reducing from C2. We only observe C2 per second. So this is an important finding. And very curiously, we found in the literature a very close example of what we have been investigating in these recent times. In a few years ago, 93 Nature, Javier Ramirez published a paper in which he used the copper one supported into a nitrogen network, in which these two copper atoms were at a distance of 400 picometers and were not active at all in the formation of coupling carbon-carbon, carbon-oxygen, carbon-nitrogen, carbon-sulfur. While if they switched to this position and the distance here was 260 picometers, they were active in carbon extra. So these figures, 400, 260, are important values. So this really means that you need to have a very well structured photocatalyst with your catalytic center at a very well defined distance if you want to have a selective productive species. Otherwise, you may have a mix of different species which will not absolutely be useful for target of our studies. We need to convert CO2 is a difficult target in a way that we spend a minimum energy. So the post-processing energy cannot be much high. Otherwise, the benefit of recycling carbon will be completely lost. Okay. So that's the target we have in this project decided. So we are now together with other colleagues. Tomorrow there will be yes, presentation by a group from Warsaw on the same topic of CO2 and water coprocessing for rich carbon-based products. They use a different strategy, but at the end of the day, it's always the same problem we have to face to construct engineered surface for using copper 1 oxide as a photocatalyst, extend its stability, have a very stable electrode which can be used for a long time. Our project, we have a target on that, and this is a key point, and I think these are points which are very common to all those who work on photoelectrode chemistry. Stability of electrodes, engineering the surface is really a matter which is a common basis for all of us. Okay? And so that's something that I did want to share with you, the problems we have faced and now we are trying to solve these problems. So is 260 picometers distance between active centers seems to be a really key distance for having the possibility of coupling carbon-carbon. Okay, and then as we are in the land of Erasmus, just to close with the sentence of Erasmus, give me 20 more years to leave the golden age. So that's a long time for me, but anyway, I'm fighting and I'm pushing in the direction of carbon recycling since the 70s, the end of the 70s, 20 more years. I will be patient. I will wait for it. Okay. Thank you very much for your attention.
Thank you very much for the very nice presentation, for pushing the research forward. Any questions? And if you have questions, please use the microphone so also our colleagues online can. So any question? You hear me?
Yes.
Good afternoon, good morning to everyone. It's a great pleasure for me to join all of you. I am Professor Konsolakis from the Technical University of Crete. Thank you very much for the insightful presentation. And I have a question about the local surface structure of copper species in order to turn the reaction to the desired products. It is clearly revealed that carbon-carbon distance is a key factor in order to control the selectivity. And I have a question about the size of copper. How the size of copper can affect the CO2 activation and then the growth of carbon in order to produce the desired products.
So in our studies, we use low nanometric copper oxide. So the size of the particles is around a few nanometers, okay? And on these particles, we have the distribution of copper. So the point is, the real point is, how to have a full coverage of the electrode with this kind of particles. This is the real key point, because if you have so small particles and they are distributed here and there in the electrode, so the efficiency of the photoelectric catalysis will be very low. So the full covering of the electrode with nanoparticles is one of the very difficult topics to deal with. And this is where we are putting particular attentions these days. So that's why we are shifting from preparing the photocatalyst and then drop casting or spray casting or whatever technique you can imagine for covering the electrode, or depositing the support on the electrode and make an electrode deposition of the catalyst. We have seen that when you make an electrode deposition of the catalyst on the support, which is on the electrode, you have a much more uniform distribution. And also there, as current does play huge role. So that's the engineering of the electrode is not an easy task, and is difficult as much as trying to find the best distance between the active centers. But that's very important.
Okay. And how is it to control the morphology of these copper nanoparticles? For example, by following different preparation synthesis routes in order to have a different population of exposed facets in the reaction environment. Thus, there is a key factor in order to control the size and at the same time the exposed facet on the. It's not an easy task, of course. I understand.
No, it's not. So, as I mentioned before, we are trying to use this fructose as a way to control the facet, okay, and also the size, the given point. Because the interesting part is that I should mention to you too is that fructose are pure silica. So once we have made the composite, which is made of the copper oxide deposited on the fructose, we can dissolve the silica and get the pure copper oxide, which has a quite uniform size for concerns, and the morphology is the same because it has been grown exactly on that fructose. So this is the way we are trying to use in order to find a solution to these huge problems, which are the dimension and also the facet morphology constant. When you have a mix, then you have loose uncertainty. You will produce C1, C2, C whatever. That's the problem. Having just one facet is not that easy, and having the correct dimension is also a topic you work Just center points.
Thank you very much.
Any other question? Yes.
At the Tonschrift Institute. Thank you very much for this nice presentation and the wonderful dependence of your morphology of your nanoparticles on the selectivity of your reaction. But your reaction is carried out in water.
Yes.
And you have, if you start with these well-defined cupric oxide morphologies, you used to have cupric oxide under the reaction conditions at the surface of the electrodes, or is this transformed to hydroxide? And what influence would this have?
In the conditions we use always basic conditions for our reactions. They stay on hydroxides. They are not converted into hydroxides. We have not observed this kind of change so far, at least under the conditions we use. If you go to lower pH, then you can have many different changes. And but working around 10 pH, you keep the oxide morphology. Those are the conditions under which you form the oxide. So that's why you can keep it.
Other questions? Yes, I'm coming.
Thank you very much. I started working on CO2 electrolysis in the last minute as well. You mentioned you're doing it in alkaline conditions. Of course, there's much more CO2 available, but most of the CO2 is bound in bicarbonate or carbonate. And I've always worried about how that works. We think about CO2, but actually most of the CO2 is not really coming from that. It's a long-standing worry of mine.
It's very important part. So anytime you use CO2, and it is over 7, almost totality of CO2 is in the form of hydrogen carbonate. So it's very difficult to understand if you are using the hydrogen carbonate as a source of carbon or CO2. So this is a key point. Okay, and we are trying to find a solution, but sincerely, I really cannot say that we are using gas CO2, because we are also trying to not pump any CO2 into the cell, photoelectrochemical cell or photochemical cell. And in that case, we also observe the formation of reduced products at a lower rate anyway. So what I think is that at the surface of the electrode, we have two species, the hydrogen carbonate, which is in solution, and this will be the highest concentration most likely, but also some free CO2, which can be in solution, but a very, very low concentration. If you look at the diagrams, the distribution of carbon species according to pH, you conclude that at pH 9, you don't have any free CO2 in solution there, or it's a very small amount. And we tried time ago to use enzymes which could convert CO2 into hydrogen carbonate and the reverse, in order to try to elucidate which was the real species which was used under the conditions we are using. But we did not find any clear results saying is this, is that. This is a point which is still open, and we are still working on that in order to understand how the reaction really goes, which is the real actor of the. We have used also carbon 13. This goes well in the gas phase when you don't have the liquid, you don't have water. In that case, we see that it's CO2, which is okay. But when you go in solution, there is a question. We're trying to find a solution to that, but we do not have the answer now. Not yet.
Right.
Thank you very much. Let's thank again the plenary speaker. And we have also a small present because we are not Dutch.
One Italian,
Yes.